много-много новых блестящих идей, ну и, конечно же, много новых успешных учеников. Ну, с Степаном Жургицевичем я знаком уже больше 20 лет. Особенно тесным знакомство стало в Боннском университете. Мы там очень часто встречались. И я признателен Седахмату за многие минуты, а может быть даже часы тесного общения с ним, очень продуктивного, за сотрудничество с ним. Большое спасибо, Седахмат. Рассчитываю на продолжение. Ну, теперь, собственно, перехожу к докладу. Ну, вот название Optimal Bounds on the Speed of Subspace Evolution. The topic of my talk is related to the so-called quantum speed limits that arise in quantum mechanics. By a quantum speed limit, one usually understands a lower bound of the time that is required for a quantum system to evolve between two distinguishable states. A natural question. We have two states, and the question is how much time the system needs to move, to evolve from one state to another one. So for simplicity, we consider the case where the measured units are shown in such a way that Planck's constant is 1, and to give an impression of what we are talking about, let us consider a quantum mechanical system with Hamiltonian H that is allowed to be arbitrary self-adjoint operator in the Gilbert space. Any operator, self-adjoint operator is allowed. The unit vectors of the Gilbert space H represent possible pure states of the system, and evolution of a state psi is governed by the Schrödinger equation. So simply you solve a Cauchy problem for the Schrödinger equation. I want to talk about the case where H may be unbounded. So in this case, we should be careful with domains. In fact, if psi 0 belongs to the domain of H, then for any time psi of t also is an element of the domain of H. So we deal with, in fact, with a unitary group u of t exponential equal exponential to the negative I h t. And the question is, how fast can the related system with the Hamiltonian H evolve to a state orthogonal to its initial state? This was first question asked just by Mandelstam and Tam long ago in 1945. How much time is needed for a state to move to an orthogonal one, to a state that is orthogonal to the original state? Clearly, this question is maybe important in various areas, in particular in quantum information, quantum computing, when we talk about the change of state of a quantum system within the computing machine. So the known answers to this question about bounds on the orthogonalization time on t perpendicular, so we use this notation for the time needed to move into the orthogonal state, are as follows. The first is the classical inequality due to Mandelstam and Tam. This inequality has the form t perpendicular is greater or equal than pi over 2 delta E. I will tell what is delta E. And much more. Latest one, Margolis-Levitin inequality of 1998 is this one, where delta E is a different quantity. So the first quantity, capital delta E, is given by this expression. That is simply the energy spread dispersion for the state psi 0, while the other quantity is the average energy for the state psi 0 measured relative to the low bound of each. So there are two basic classical estimates. In 1973, without fanfares, extension of the Mandelstam bound was discovered by Fleming. So who says that T theta is greater or equal than theta over delta E, where T theta is the time moment at which the acute angle between the initial state and state psi of T, given of course by this natural expression, between the vector psi 0 and psi of T, reaches some value theta in the interval 0 pi over 2. So this is, we call Mandelstam Fleming bound. One should say that all the bounds, also very different, for example, this one are very different bounds, are proven to be sharp, are proven to be optimal. During this time from 1945, many other people discovered the Mandelstam inequality. In addition, there were many generalizations done for mixed states, recently for some states in thermodynamics. So this is already a long story, and many papers have been written on this subject. Here, I don't know, maybe this file survives in the and will be presented somewhere. So I refer to the review articles, Daphne Campbell, Frey, Bender Brody, and also a recent paper, Lin and Luchkovsky. And what I will talk about, I will present the results obtained jointly with Sergio Ribeiro, mainly in this second paper that just published. So what we are doing, what do we do? Instead of a state, instead of a vector, we want to consider the whole subspace of a Hilbert space and want to address the same question. If we start with a subspace, how much time is needed for this subspace to go to specific position with respect to the original subspace? So we discuss the question of evolution of a subspace. Or, in other words, we consider subspace pi 0. Every vector in this subspace, of course, intersection of with domain of H, is developed according to the Schrödinger equation. So we consider family of Cauchy problems, and then study what happens to the spans of the vector psi over T at any given moment T later on. So the only restrictions that we use, we consider, we require the invariance of domain of H under the projection pi 0 onto this subspace. So pi 0, this capital pi, is a projection operator, projection onto this the space pi 0 that we studied. Okay, in this case, the Hamiltonian may be presented in the block matrix form. So very nice structure. So due to this property, due to this requirement, and this simplifies our work in the case of unbounded H. So what do we do? So we consider the range of the projection P of T that are denoted by P German of T, and P of T is simply the result of the evolution of the projection of pi of P0. So this operator. And okay. So of course, in this case, we know that the projection P of T is a solution to this operator Cauchy problem where pH in square brackets is the commutator of the operator P of T and H. And if we will discuss only the case of bounding H, then we can forget about everything. It is very easy to talk about, because in this case, P of T is differentiable with respect to the operator norm, and presentation is very simple. But in general, we discuss the strong solutions to these equations if H is unbounded. So the problem. So we want to measure the position of evolved space with respect to the original one. How to do this? What is the measure of the closeness between the subspaces? Of course, the starting point is a very, I would say, naive point, is simply to consider the usual operator norm. That is, if we have two subspaces, Q and R German, then we consider projections onto these subspaces and simply take as a distance between these subspaces the norm of this difference. Of course, this is a very nice metric, but unfortunately not optimal when we discuss the evolution problem of subspaces. And of course, it's very easy to obtain answer. You see, in the left case, in the left-hand side, we have the derivative. On the right-hand side, we have P of H, commutator of P and H. And then we immediately obtain an answer. So with using this distance, we have the following result. Suppose that H and P0 with domain of HP0 equal domain of H is a bounded operator. That is such inequality holds. Then the closure of H and PT is a bounded operator on the whole space. And if we introduce this quantity, so we have already introduced this quantity, then the distance, the norm of the difference between P and T and PS is less than or equal than the product of this quantity V of HP0 times T minus S for any T and S and R. So notation, of course, notation V points out that we assume that this V is just the speed, velocity. So notation is very natural. But we prove that in fact there is much stronger estimate for this quantity, for this quantity PT minus PS through the difference T minus S than in this inequality. To this end, I should recall, to make propaganda of another metric on the space, on the space of all subspaces of H, on the set of all subspaces of H. This is another very nice metric, in fact. This metric is associated with the following quantity. So instead of the norm of Q minus R, the difference between two projections, we take R sine of this norm, quite unexpectedly. This quantity, was angle between the subspaces that are ranges of Q and R, is called the maximal angle between these subspaces. No, this is already quite old story, so that the maximal angle is the metric has been proven in 1993 by Lawrence Brown. So I also would like to refer to the very nice discussion presented by Albert Zilman and Konstantin Makarov in their paper on Journal for Foreign Anglophone Mathematics in 2015. So if you want to learn something about this metric, I would suggest to address to these papers. So why this quantity has the meaning of angle? It's very simple. So if we perform easy computations, then Q minus R squared, you will find that Q minus R squared is simply this quantity. So Q perpendicular is 1 minus Q, so complementary projection. So Q minus R squared has such a form. That is, it is block diagonal with respect to this decomposition, R and R perpendicular. This inequality means that Q minus R in fact has the following norm: either this one or this one, maximum of these two quantities. That is, in fact, maximum of these two norms. Look, for example, into this norm. What is this in the case where R and Q are simply lines on the plane? So, of course, when you compute the norm, you need to start from a vector that is located on the space R. Because if you take other, we make lose some information. So the compute norm, you start from a vector in R. And what is here? We take a vector in R and perform projection. So, and if theta is normal usual angle between two lines, acute angle, then we see that the norm of Q perpendicular R is just the sine of this theta. So this quite natural quantity. In fact, this is a generalization of the angle between lines to arbitrary subspaces in Hilbert spaces. In fact, there are operator angles, there's a big machinery, a big theory on the subject, but we use only maximal angle. Okay. Of course, the maximal angle has also quite a long story. I would refer to the works Krenk, Krasnosersky, and Milman of 1940, where they introduced a quantity very similar to the maximal angle. Of course, we can give quantum mechanical interpretation to the maximal angle, but if you wish, you can go to the paper and to study this there, because of course it's not so simple to present this interpretation immediately in a nice way. So what do we do then? So since theta is a metric, the maximum is the metric, we simply do the following. We use the triangle inequality several times. So we perform a partition of the interval between S and T, 2 points on the real axis, and obtain such an estimate for theta, Qs, and Qt. In the case where Q of T is piecewise norm, piecewise smooth with respect to the Pareto norm, from here making a limit transition, we arrive at such a formula where Q dot of tau is the derivative, the time derivative of Q. But this statement, it works well also in the case where Q is not differentiable in the operator norm sense, but only in the strong sense. So we also can prove such an inequality. Okay. So roughly speaking, we use this formula. And immediately from applying this formula, we obtain the following result. What was the theta? Theta is arcsine PS minus PT. Therefore, we have the following result. Angle between the subspaces PS and PT, that is arcsine PS minus PT, P capital minus P capital T, is bounded by this product. instead of simply PS minus PT, we have arcsign here. Arcsign is bigger than simply the argument, and therefore it suppresses the difference PS minus PT. It is much stronger estimate than the original one, than this naive estimate. You see, here we had simply T minus PS on the left hand side, but now we, instead of the normal P minus PS, we have arcsign here, much stronger suppression. Okay. No, in fact, this quantity, maybe remember, I told that our Hamiltonian has a block matrix representation with respect to the partition pi 0 plus pi perpendicular. And in fact, only the off-diagonal elements are responsible for the variation of subspace. So subspace is governed by the off-diagonal elements of H. I skip this presentation. Okay. But you remember, as a Mandelstam term inequality or Mandelstam term Fleming inequality have such a form. But by now, we do not yet have such a form. You see, the C theta is greater or equal than C over T over delta E in the Mandelstam term Fleming inequality. We have simply some very generic bound that applies in fact to many other problems, not only Schrodinger equation, of course. Any evolution of arbitrary subspace is governed by unity family. So the question, is it possible to obtain from this inequality something we calling Mandelstam term inequality? Answer is yes. The answer is the following. Assume that at tau equals C theta, the maximal angle between the initial subspace is 0 and the subspace in the path P tau reaches the value of theta that does not exceed pi over 2. That is such equality holds. Then this time satisfies the following bound. So this is still not yet Mandelstam term equation. It is sharp bound effect, No, only one step remains. Only one step remains to Mandelstam term Fleming-like bounds. Here I would like to talk about the example I would like to take. Would like to tell that there is a very simple example that shows that all the bounds above are optimal. This example is simply a two-level quantum system that two-dimensional Hamiltonian that has two binding energies, two eigenvalues E1 and E2. So, and if we take the subspace spanned by the vector E equal 1 over square of 2, E1 plus E2, where E1 and E2 are the eigenvectors, and then we will find that all the inequalities we wrote turn into equalities. That's all the bounds are optimal. So next step, just when we come to the Mandelstam time Fleming-like bound. So from this bound, by estimating VH P0.
Professor Motovilov, You have time already.
Ага.
Okay,
So
just
we
two,
obtain
two-
such a bound
two more
where,
minutes, please.
where this quantity is the energy span over the space P0. So, and the last bound is related to the case where we know something about the spectrum. If you know that our H is bounded and its spectrum is in the interval m small m capital, then we can present such an estimate for the time c theta. So thank you very much. That's it.
Okay. Please, questions. Yes, please, but.
The main assumption is that the projection matches the main that you made.
Yes, yes. Then there will be big troubles.
I understand that you
Mhm.
cannot get very little data.
Surely, but at the moment, no progress in this direction.
Because apparently you are applying some
Uh-huh.
variant of central limit theory,
I see.
in my opinion.
I didn't know. So in fact, the progress has been done to the time-dependent Hamiltonians. So the next step is to extend these bounds to the case where the Hamiltonian depends on time.
Okay, any more questions? Yes, please.
I think so. If you choose not arbitrary Hamiltonian, but some specific, in this case, you will obtain a partial version of quantum speed limits for the particular family of Hamiltonians. In fact, people do this. So yeah, but we can say simply generic situation. We didn't specify Hamiltonians at all. Hamiltonians H could be arbitrary self-adjoint operator. Да, пожалуйста. Сейчас.
Метрика псевдоевклидового пространства. Не попробовали определять вот эти понятия?
Метрика всех каких пространств?
Ну, пространство теории относительности.
А в теории относительности?
Да, да.
Ага.
Не положительно определенной метрики. У вас напрашивается вот это как раз является метрикой теории евклидового пространства.
Очень интересный вопрос. Хотелось бы его понять поточнее, может быть, после сказать,
Пожалуйста.
Я думаю, можно этот вопрос
Покажите,
в рабочем
пожалуйста,
порядке.
формулу
Абдулазык.
в начале формула. Это как раз формула плоскостемьковского. Поэтому, вернее, плоскостемьковского. Очень хорошо. Вот эти пергамент.
Все, да, тогда в рабочем порядке можете обсудить. Есть еще вопросы?